Hello everyone. In today's video, we're going to be covering structure 1.3, electronic configurations for SL and HL chemistry. This is what we're going to be going over in today's slideshow. So the SL content is highlighted in blue and the HL content is highlighted in red. So SL students, please feel free to click off by the end of the SL content. Let's start with the electromagnetic spectrum. You guys should be familiar with it because we covered it in GCSE. You should be familiar with the fact that gamma is the wave with the highest energy because it has the shortest wavelength and highest frequency, and the radio waves are the lowest energy type of wave because it is the longest wavelength and the lowest frequency. And in this capacity, you need to know two equations in this topic. The first equation is C equals F lambda, where C is the speed of light, F is frequency, and lambda is wavelength. And the second equation is E equals HF. E is energy, H is Planck's constant, and F is frequency. And this proves that high frequency UV light carries significantly more energy than low frequency infrared. Now, let's move on to emission spectra and evidence for quantization. So, as you can see here, there are two spectra that you need to know in the course: continuous spectra and line spectra. So a continuous spectrum shows all wavelengths of visible light with no gaps, whereas a line spectrum it consists of discrete sharp lines of specific colors. And what does this mean? If electrons could move between any energy value, we would see a continuous rainbow. But because we only see specific lines, we know that electron energy levels are quantized. What does that mean? Well, it means that each line represents a specific step an electron takes when falling from a higher energy state to a lower one. So electron energy levels exist at specific energies. And how does this play into the broader scheme of things? Well, we can use the hydrogen series as an example. So for hydrogen, if let's say there's an electron on any energy level higher than n equals 1. Let's say that electron fell to the energy level n equals 1. This forms the Lyman series, and consequently, this would emit UV radiation. When an electron transitions to n equals 2, this is the Balmer series, and this would release visible light. And when an electron falls to n equals 3, this is the Paschen series, and this releases infrared radiation. It's really important that you guys memorize this, okay? And you guys might also see that the energy levels, as you look at the top of the diagram, they get closer together. And this is known as convergence. And this is because as the principal quantum number n increases, the energy levels get closer together, eventually converging at n equals infinity. This convergence limit is the point at which the electron is expelled from the atom. It's known as ionization energy. Now we're going to look at energy levels, sublevels, and orbitals. So we have moved past orbits, which imply a fixed circular path, to orbitals. Now, an orbital is a mathematical wave function, but what you need to know is that it's basically a region of space where you would find an electron. You could think of it as a cloud of electron density. And this is determined by the principal quantum number, which defines the main energy level, where total electron capacity is denoted by the equation 2n squared. So if you wanted to find the maximum number of electrons for the energy level n equals 3, you would just substitute 3 in. That would give you 2 times 3 squared, and that would give you 18 electrons. Now, I just described what orbitals were, and I'm going to describe them in even more detail. So, as you can see here, there are 4 types of orbitals: S, P, D, and F. And as you move up these orbitals, you will see that the F orbital has the most energy and the S orbital has the least energy. So how do you actually represent orbitals within these specific subshells? Well, you draw a box, and this box can only hold 2 electrons. So the S subshell would have 1 orbital, 2 electrons. The P subshell would have 3 with 6 electrons. The D subshell would have 5, and I'm sure, as you would guess, it would be 10 electrons total. And the F subshell would have 14 electrons maximum because it has 7 orbitals. I'm just going to fill these in first. Now, you guys also need to know the shape of these orbitals. As you can see here, the s orbital is spherical, and the p orbitals are dumbbell shaped. It's just how you would describe it, essentially. And there are 3 perpendicular orientations, because if you fit this onto an axis, and we draw all 3 axes. The y, z, and x axis. You can see that for, let's say it was a px type orbital, that would exist parallel to the x-axis. It was py, then it would go straight up because it's parallel to the y-axis. And I'm sure you can guess, pz would be parallel to the z-axis. And we're gonna go more into how you can actually write these electron configurations. So, you need to know 3 principles. The first principle is the Aufbau Principle. And essentially, it means that you have to fill orbitals starting from the lowest energy level first. So that means to say that you can't just fill a 3s or a 3p first. You would have to start with 1s, which has a maximum of 2 electrons. So that would be 1s2, moving to 2s2, 2p6, and so forth. Now, the second rule is Hund's rule. Hund's rule essentially states that electrons have to occupy degenerate orbitals singly first, with parallel spins to minimize repulsion. So that means you would have to fill, let's say you had 4 electrons to go around. You wouldn't fill it like this, okay? You wouldn't fill it orbital by orbital. You would have to fill it singly first. And the 4th electron would have a different spin to this first electron so as to minimize repulsion. And the third principle is the Pauli Exclusion Principle. Essentially, it just means an orbital can have a maximum of 2 electrons. And also, it's really important to know that for transition metals, which is the middle block of the periodic table, 4s electrons are lost before 3d electrons. So let's say something had 4s 3d8. You wouldn't lose the d electrons first. You would lose the 4s2 electrons first, and then you'd be left with 3d8. And also memorize these exceptions, please. It's really important. Chromium is an exception because, you know, a half-filled d subshell is more stable, and copper is also an exception because a full d subshell is more stable for transition metals. Now let's practice filling orbitals. Let's say you wanted to find the electronic configuration for potassium. This means that you would have to kind of count the electrons in each box, right? So first you'd start with 1s, you'd move to 2s, 2s2, 2 electrons. And then you move to 2p, that would give you 2p6. Then you'd move to 3s, and then subsequently 3p6. And then you find potassium here, which is at 4s1. Okay, just count the number of boxes essentially, and that will give you the number of electrons per subshell. And what you also need to know about is the trends in successive ionization energies. So you can see here, every subsequent electron removal requires more and more energy because you're removing a negative charge from an increasingly positive ion. And you can see here that there are some discrepancies, particularly between beryllium and boron and nitrogen and oxygen. The dip from beryllium to boron proves that the 2p subshell is higher in energy than the 2s subshell. And the dip from nitrogen to oxygen proves spin pair repulsion, which means that the paired electrons in oxygen's 2p orbital repel each other, making them easier to remove. So you should always kind of anchor, let's say you're answering a question on this, you should anchor your answer in nuclear charge, distance, shielding, and spin pair repulsion. Now, we're going to use the equations, the two fundamental equations, along with some others, to kind of answer a question. So it says here, the convergence limit for the hydrogen atom has a wavelength of 91.16 nanometers. Calculate the ionization energy for hydrogen in the kilojoules per mole. Highlight the units first, okay? The first equation that we're going to use is C equals F lambda. And we're going to rearrange this to find frequency. F equals C over lambda. Now, we're going to plug in the values which were mentioned in the question, okay? So that would come out to the speed of light, which is found in your data booklet, 3 times 10 to the power of 8, divided by 91.16 times 10 to the minus 9. And you might notice, why did I put a 10 to the power of minus 9 here? Well, it's because wavelength is given in meters, and this is given in nanometers. So this will give us an answer of 3.29 times 10 to the 15 seconds to the power of minus 1. Now that we have frequency, we can calculate energy. Energy equals HF. Use the equation here. So you would plug that in. You're given H in your data booklet. H is 6.63 times 10 to the negative 34. Don't memorize that, don't bother. And you use your value for frequency that you got down here, 3.29 times 10 to the 15. And that would give you 2.18 times 10 to the negative 18 joules per atom. And now we're supposed to calculate ionization energy for 1 mole of hydrogen atoms, but we're only calculating the energy per atom, as you can see here. So what we're going to need to do is, you might have guessed, multiply it by Avogadro's constant. So that's just, you should remember that it is 6.02 times 10 to the 23. And then you get the answer 1,313,491 joules per mole. But it asks for kilojoules per mole. So you just divide that by 10, and you'd end up with 1,313 kilojoules per mole. And that brings us to the end of the topic. Now, if you like this video, please make sure to drop a like and subscribe to Project 45. It would really help us grow the channel. And as always, thank you guys for watching.